We now look into some example models for the analysis or synthesis of spatial configurations. The first one is the von Thünen model, which was introduced by Heinrich von Thünen in 1826. The land use or the use which a piece of land is put to is a function of the cost of transport to market from this piece of land, the market price that you can achieve with a certain product or use, and production cost of the product the land rent a farmer can afford to pay, which is determined by yield. So you can see the detailed formula on the slides behind me. It can be illustrated by the bit rent model, which is well-known geographical economic theory that is based on the von Thünen model as illustrated on the right side of the slide. It shows the ideal land use or the ideal agricultural product that you put onto a piece of land independent to the distance to a market, which is usually located in the center, so either in the center of these rings or at the origin of the diagram where you see these bit rent curves. And always the production that you put, the use that you put on a piece of land changes after these curves intersect with each other. So you always use the product with the highest return, so the highest profit, and this is always the line above all the other lines. And where they intersect, you change to another project in this diagram. The original model generated 4 concentric rings, as you can see in the illustration as well, of agricultural activity. For example, dairying and intensive farming lies closest to the city. Since vegetables, fruit, milk and other dairy products must get to the market quickly, they would be produced close to the city. The emerging land use pattern would be rings around the central market, but they can be distorted by streets or rivers that have an influence on the transportation costs to the distance or the distance measured in time, so which is more or less both the same. Next, we will look at a generative model that is developed to synthesize floor plans more or less automatically. Based on an evolutionary algorithm, it minimizes the overlapping of rooms that you randomly put into a boundary in order to create a dense packing of these rooms, so without any overlaps or gaps between them. At the same time, the algorithm tries to minimize the distances of rooms that are defined to be neighboring to each other's as by means of this topographic diagram that you can see by the connections of this, or drawn by the lines between the rooms. So where you have a line between 2 rooms, they have to be neighboring, means they have to have a door from one to the other room. These objectives can be formulated in a mathematical form, why we call it a formal model. So we can use an optimization method to solve this formula, or to minimize it or maximize it. Nevertheless, it's a very formal model in the background. It offers a certain level of interactivity, while it always tries to come up with a satisfying geometric solution. So the user of this model can formulate requirements, and you can also interact with the geometrical representation of the rooms or the connections, and the model tries always to adapt to the new requirements by a user. So it's a very interactive and flexible model, whereas it's based on a very rigid formal model. So a formal model does not mean that something is not very creative or flexible. Another very important spatial model is the model that describes the distribution of central places. In geography, central places can be cities in a country or region, or centers inside a city. The sizes and distribution of these centers follow some relatively universal principles. One of these principles is, for example, the marketing principle. According to the marketing principle, the market area of a higher order place, or node as drawn in this illustration, occupies 1/3 of the market area of each of the consecutive lower-sized neighboring places, or the nodes. The lower-sized nodes, which are 6 in numbers, of the second largest cities around this arranged on the circle, are located at the corner of the larger hexagon. However, also in this marketing network, the distances that you have to travel from one center to the other is minimized. The transport network itself is not the most efficient one because there are no intersections or intermediate transport links in the network between the larger places or between the nodes. So no streets intersect where you don't have a city or a node. Therefore, there is the traffic principle as illustrated on the slides as well. For another aspect, we also have the administrative principle, which results in a slightly modified pattern, but they all share more or less the same logic, which creates this very regular pattern with a hierarchical order of centers distributed in space. The central place model has been developed by Walter Christaller, who proved it empirically by the distribution of cities in southern Germany in 1933. There are primary centers like Munich, Nuremberg, Stuttgart or Zurich, which are surrounded by secondary local centers, as you can see this on this drawing behind me. Also, the ideal pattern of the market principle, as shown on the right side, is distorted by topographical conditions, so you may have mountains, or you may have rivers, or the locations of resources. So all these aspects can distort this ideal pattern, but the spatial hierarchy and the general arrangement of these centers as described in the model, they are evidently, you can find them in this pattern, so it's evident that this model works in this case. The central place model was developed based on an analytical investigation, as shown in before by Walter Christaller. Therefore, it is usually applied to describe the distribution of centers based on the inherent spatial economic conditions of an efficient distribution of central functions. So it is assumed that the economic forces created these patterns in a kind of a self-organizing process. So this means that the central functions like big hospitals or theaters, the economic logic says that it's only efficient to place them in higher order centers. So you don't go every day to the hospital or to the theater, so you have to travel a longer distance. But the functions that are not that central, like things you need on a daily basis, they are distributed more equally also in the subcenters. So that's a kind of economic logic and corresponding forces to distribute certain centers. Nevertheless, the central place model has also been used for the planning of small towns and villages, for example, on the Dutch polder. So not only the analysis works with this model, it can also be used for planning. Between 1937 and 1942, an area of 48,000 hectares was reclaimed from the sea and turned into a polder in the center of the Netherlands. The layout of the new locations in the polder is mapped in the illustration, looked very much like the central place layout. The planned sizes of the centers is shown on the table, where we can find a clear primary center, so the biggest city with the most inhabitants, planned and also in the real numbers that you can see. The work is the central place that is supported by the lower order centers around it. So basically, the hierarchical order of the center with the supporting villages, this worked very well, whereas of course in reality it developed a little bit different. But you see, it's a nice example that you can use the central place model also as a kind of a planning tool. In the next slide, you get an impression that you can also, or that the information that different models can give you may also be interlinked a little bit with each others. So for example, by using the space syntax model to analyze the centralities in a street network of Switzerland, as you can see it in this image, we can detect a pattern of centers following the central place model. So the space syntax model shows you where you find the places that are closest to most or to many other places. They are the brighter locations in this image, and the darker blue ones, they are not that central. So also here you see a distribution of cores of centers, which may have a similar logic as the central place theory from Walter Christaller. The reason for looking at all of these very rational, analytical and synthetical models in this chapter is that we want to give you a good basis for working with more advanced and sophisticated simulations and modeling tools later on. The quote from Berkel and Bose is a nice reflection on this idea. The first trap is the one that you might get into as a student. Parametric design techniques have brought the technical to the forefront, the desired result out of focus, and deadly homogeneous wealth of avant-garde designs. Means we sometimes run into the danger to be fascinated from the possibilities of simulation models or parametric tools and modeling techniques, and sometimes we may forget why we use all of these tools and techniques and to achieve a better, a more sustainable, a more livable built environment, which we always have to keep in mind. And therefore, we look into the theory of models, of modeling, that you always have a very nice foundation to reflect the ideas of how to use models in the right way.